In this video, we'll talk about ohmic materials and Ohm's law. George Simon Ohm showed that for some materials, the current that flows through the material is directly proportional to the potential difference across that material. Such materials are called ohmic materials after Ohm. So here's an example of a 4-point probe testing device in which there is a power supply of some sort that can be adjusted to supply different voltages. And the charges come out of here, go through an ammeter, and then if we had a perfect device, we'd have a voltmeter such that no current was allowed to go up in it. Turns out no voltmeter is actually that good, but they're very close. So most of the current, if not all of it, goes through my test material. And if I'm assuming, as I said, that no current goes this way, then the meter that I'm reading on the ammeter for the current is the current going through the test material. And then it comes back down and goes into the supply. And I measure the voltage across that test material. If you find that when you do this experiment and you plot the voltage against the current, either the voltage on the Y and the current on the X, or you can do it in the other way often, where you plot the current on the Y and the voltage on the X, since I'm controlling, in this case, the voltage in the supply, although there are current supplies that you can buy. Then if I plot this voltage versus current and I get a straight line, that material is an ohmic material. But there are many materials that when you plot that, you do not get this. You get something that looks like that, or maybe some other curve. Those are simply known as non-ohmic. The so-called Ohm's Law that we're going to talk about for resistors only hold for materials that have this relationship. It's not a law. Most materials do not behave this way. Ohm's law is a relationship only for these special materials called ohmic materials. So it really should never have been called law. All right? The only way to know if you have an ohmic material or non-ohmic material is in fact to measure the voltage current curve, also known as the IV curve. Now, let's look at some materials that are ohmic. Things that are ohmic, when you put them in electrical systems, are called resistors. And the property of the resistor that's of interest to us is the slope of the voltage current graph, if you plot it this way. That slope, straight line, goes through zero. The property we need to know that makes lines different, whether they go like this or they go like that, is what is their slope. However, if you plot it at IV, then this thing we're going to call resistance is going to be 1 over that slope because you plotted it in the other direction. Okay? So resistance is a measure of a material's resistance to the flow of charge through the material and is the slope for this type of graph where you plot V along the Y and I along the X. And we can put it in the following way. We could say that VR is equal to voltage divided by current. And the slope on our VI graph. Now it turns out that this resistance is not just a property of the material. All right? If in fact you make it out of copper and you make the copper of different sizes, you get different slopes when you test them. So if we're going to plot that, we're going to have to find something else that's unique to the copper and not the shape of the copper or how big the copper is, or whether I used gold and made it 2 inches or copper and made it 6 inches. We'll find that in a minute. However, for an ohmic material of fixed dimensions, so if you didn't change the size of the object, the resistance is constant for a given temperature. So there's really two things that can affect that slope. One is the size of the material, and the other one is the temperature. And we'll come back and talk a little bit more about that in a minute. The unit of resistance is called the ohm, again because of George Simon, and it's given the symbol of a capital omega. Now, kind of interesting, resistance is how hard it is for things to flow. Think of water. If you make the pipe through which the water flows smaller and smaller, it's harder for the water to go through the pipe. If you look at the opposite, not how hard it is to flow, but how easy it is to flow, that's called conductance. And the units for that are called the MOHO. Now, they got a new unit form in SI, but interestingly enough, they call them MOHO, and they're MHO. It's ohm spelled backwards. Kind of a little trivia for you. A resistor is any element that transfers electrical energy into heat or mechanical energy while obeying Ohm's law. In other words, we had capacitors. Capacitors try to store energy. We have batteries that give energy to a system. We'll find later we have inductors which store energy but store it in a magnetic field rather than an electric field. Resistors are where you convert that energy into something else. Their symbol is this. They have an R that tells you that what that slope of that IV curve would be. And if the current is going this direction, and if you have your voltmeter lead set up so it goes into the plus and out the minus, then Ohm's law is written as V equal IR. Why did I say if you do it this way? Well, because you, of course, could have put your voltmeter leads in a different direction. You might have written them like this. Maybe the current's coming in this way, but you chose to put your voltmeter leads the other direction. Well, in that case, the voltage formula is minus IR. It's flipped because I have flipped the leads of the voltmeter. I have reversed the limits of the integration when I'm integrating over the electric field. And when you flip the limits of integration, you flip the sign of the integral. So this is important later when we start adding up voltages. You're allowed to put these plus and minus leads any way you want, but you have to calculating the voltage related to the current, you have to make sure you do it correctly based upon the way you've chosen your signs. Let me put my I here for this current. There we go. As an example, what is the resistance of material if you measure a voltage drop of 10 volts when 4 milliamps of current flows through it? Well, R would be 10 volts over 4 milliamps. 10 over 4 is 2.5. A volt over a milliamp is a kilo ohm. 2,500 ohms. Here's a different problem. What is the voltage drop across a 6 kΩ resistor in the following circuit? Well, what's important here is what we learned earlier about being in series. These two elements, this power supply and that resistor, are in series. So I know there's 4 milliamps in this constant current supply. If it's in series, there's 4 milliamps going through this resistor. But this resistor is in series with that resistor. So there is also 4 milliamps going into this resistor. Well, the voltage across that resistor, and the I is going into the plus, is a positive Ri. So I have 6 kiloohms times 4 milliamps. 6 times 4 is 24. A k-ohm times a milliamp is simply a volt. So Ohm's law is very easy to work, very easy to use, provided you understand these basic ideas of current and resistance. These resistors come to you, you buy them in a package, and they have a color coding on them that you'll learn in lab that tells you what their values are. So once they've been manufactured and made, as long as you don't change the temperature much, you keep them in a regular room, you know their resistance, and if you know the current going through them, you can determine the voltage across them. Or if you use a voltmeter, you can measure the voltage, and if you know the resistance, you can determine the current going through them using Ohm's Law. Very powerful formula, very powerful idea, but it's really not a law. If you apply Ohm's Law to capacitors, you get them wrong. If you apply Ohm's Law to non-ohmic materials, you get it wrong. You got to make sure that what you're working with is an ohmic material, and in circuits, that means we're calling them resistors. All right, we'll talk to you on another video.